Hello students, welcome to the class. Today we will see the NCERT chapter 3 classification of elements and periodicity in properties NCERT Exemplar. So this is the disclaimer. Now the total number of questions in the NCERT Exemplar is given here. Out of that we will cover 11 questions. Their indexing is given in the last line. So here is your first question. Consider the isoelectronic species Na plus, Mg2 plus, F minus, O2 minus. What is the correct order of increasing length of their radii? 4 options are given here. So your time to solve this question starts now. You have to only predict the order of radii. So what will be the correct answer? It will be option number B. Okay, how we are saying that? So the basic idea behind this question is, for isoelectronic species, your ionic radius is inversely proportional to the integral value of charge. Now, if you consider all the species given in the question, then the first one is O2 minus, then F minus, and Na plus and Mg2 plus. So this is the increasing order of the nuclear charge. You can see it. The value, integral value is increasing from 2 negative to 2 positive. So the ionic radius will be opposite to this order. Therefore, we get the order of ionic radius as Mg2 plus, Na plus, F minus, and O2 minus. Our next question, the order of screening effect of electrons of s, p, d and f orbitals of a given shell of an atom on its outer shell electron is. So 4 sequences are given here. Your time to solve this question starts now. You have to arrange all these subshells in the decreasing order of screening effect. So your time is up. The correct answer will be option A. So the most efficient in screening would be A. In A would be S, then P, then D, and lastly F. How are we saying that? For that, you should remember this simple thing, that the penetration effect and the screening effect are proportional to each other. Therefore, since the penetration effect of S is the most, then comes your P, then comes your D, and lastly your F. So that same order will be followed for the screening effect as well. If we are following that, we can easily say that your S electron is the most efficient in shielding. Then comes your P and D and F. Now the question arises, what is the logic behind it, or what is the theoretical aspect behind this saying? So when we are saying that your S is more penetrated, then comes your P, then comes your D, and then comes your F, it clarifies that your S subshell is present more closer to the nucleus, or it spends more time near the nucleus. If it is spending more time near the nucleus, as a result, it will be able to shield the outer electrons in a much more efficient way. Okay, so that is the reason your penetration effect is directly proportional to the screening effect. Now that being said, we can say that the order of penetration effect is similar to the order of screening effect, which is S, P, D and F. So just wait for a while. I will come back with the session. Okay, here is your next question. The electronic configuration of gadolinium, atomic number 64 is. So 4 electronic configurations are given here. Now many of you would get confused about how we would write the atomic number of such large element. I would say element of large atomic number. So there is a very silly trick behind this. Your time to solve this question starts now. For your hint, I am saying that your gadolinium belongs to the lanthanoid and actinoid series, means the inner transition element series. Now, if you know that, then you will be easily able to determine the answer for the given question. What will be the correct answer for this question? Configuration of this, say, gadolinium. Okay, your time is up. Let us see how we can solve it. Okay, so what would be the answer for this? Okay, so what would be the answer for this question? The answer will be C. Now, why I am saying that? You do not need to remember all of this configuration, especially in the case of this question. So, the simple logic behind this question is that you should remember that gadolinium belongs to the lanthanoids. Okay, gadolinium belongs to the lanthanoids. If this is true, then from the general electronic configuration of lanthanoids, we can write that the D subshell can max have an electron of 1. Now, out of those 4 options, you will clearly see that only one option is there which has D electron less than 2, as according to the general electronic configuration of lanthanoid. Now, without attempting or without writing the electronic configuration, you can easily predict the electronic configuration of gadolinium. So, the main kick part behind this question was this general electronic configuration. See, it is D01. And there is only one option which is satisfying this general electronic configuration. With this said, I have written here that only in option A, the D subshell contains a maximum of 1 electron in the inner transition element. And hence, the electronic configuration will be xenon, 4f7, 5d1 and 6s2. So I guess this trick part is clear to you. What I said about this general electronic configuration related to lanthanoids. Okay, you should remember that, right? So now this is true for the actinoids also. If you remember, only the principal energy level will change accordingly. Now moving on to the next question. Among halogens, the correct amount of energy released in electron gain enthalpy is. So 4 options are given here. Now remember, you have to arrange them in the increasing or decreasing order of amount of energy released, right? So that is the question. Your time to solve this question starts now. Again, remember, this is an exception, okay? This is an exception question. First of all, just tell me which of these elements will easily accept the electron out of fluorine, chlorine, bromine and iodine. Which one will easily accept the electron? So your correct answer should be chlorine. Okay, chlorine will accept it more easily. We have already talked about this in the previous class where we have discussed about this anomaly, right? Now, if this is true, then what we can say that the correct answer will be C. Okay, so your chlorine would be more efficient. Then we will follow the general trend, that is fluorine, bromine and iodine. Now let us try to understand this part. What is the meaning of energy released? So if we are saying that we have to arrange them in order of energy released, then we have to only consider the magnitude of electron gain enthalpy. We do not need to consider the, say, your sign, whether it is positive and negative. We don't have to worry. We only have to see that which one is releasing more energy. That's it. That said, next what we see, the general trend says that electron gain enthalpy become less and less negative as we go down the group. And the reason behind it is that your size increases from fluorine to iodine, and hence the atoms accept electron in a more difficult manner as we go down the group, because the size of the atom is increasing and hence the energy released is getting lesser and lesser. So we can say that the magnitude of released energy also decreases down the group if the negative part is decreasing. But if we are saying this thing as the exact trend, then our expected trend would be fluorine, chlorine, bromine and iodine. So that is the normal trend which you will refer to according to the given information or according to the general trend. But what we see a exception, and the exception is due to the small size of the second period elements. You have already seen that your second period elements are very small in size, and they also display the diagonal relationship due to this small size. Okay, now here the diagonal relationship has nothing to do with the electron gain enthalpy, but your small size does. What it does? So due to this small size, your chlorine atom is easily able to accept the electron. Okay, so your fluorine is very small, therefore it will experience a very greater electron repulsion, and hence your chlorine will be facing an easy path to accept that electron. Okay, so what we can say, that the size of fluorine is lesser than the chlorine, and hence the added electron faces strong repulsion in case of fluorine, and as a result the electron gain enthalpy become less negative in case of fluorine. Therefore you get the exception of fluorine having less negative value of electron gain enthalpy than that of chlorine, and as a result your actual trend looks like this. So I guess this part is clear to you. Now I have a question for you. A similar anomaly is seen for one more I would say electron gain enthalpy trend, which is related to another group, not the halogens group. So what is that anomaly? So I am giving you a hint. It is related to the chalcogens. Okay, in chalcogens also there is an anomaly. There also we don't get the normal trend. So what is that exception? You can just think about it. Meanwhile, moving on to the next question. Which of the following is the correct order of size of the given species? Yes, the correct answer will be oxygen and sulfur. So oxygen and sulfur also faces the same difficulty, and as a result your sulfur has more negative value of electron gain enthalpy than your oxygen. So both of this faces the same difficulty. Now coming back to this question, you have to arrange them in the order of decreasing size. So it is an easy one, I guess. Your time to solve this question starts now. Okay, moving on to the answer. The correct answer will be option number D. Okay, option number D. I minus is having the greatest radius, then the I plus. Now why it is so? The reason is very simple. Remember these 2 points. Okay, it is very important to remember that your cation is always smaller than its parent atom. First this, and second that your anion is always larger than its parent atom. Okay, I think it is easy to get this point. Again I am repeating it. Your cation is always smaller than its parent atom, and anion is always larger than its parent atom. Right? If you don't know that part, then you can again refer to this simple analogy, that your order of size. Now in this case we are not considering for the isoelectronic species, but for the identical species. Okay, so these three are iodines. Now if the same atom is there and the charge is varying, okay, with different charges, then the size is inversely proportional to again the integral nuclear charge. What is the reason behind it? So your I negative is having more electrons. As a result, there will be electron repulsion, and hence the size will increase. Whereas in case of the cation, where the number of electron is less, but the number of proton is more, your size diminishes. And hence, the order of nuclear charge is in this way: -1, 0, and +1. Therefore, your order of size will be I minus, then your normal iodine, and the positively charged iodine. I guess this is clear to all of you. It's quite simple to understand, right? Now moving on to the next question. Remember, this is a more than one type options. Okay, so there will be options which are correct, right? So more than one options can be correct in this coming questions. So the first question is, those elements impart color to the flame on heating in it. The atoms of which require low energy for the ionization, that is your absorb energy in the visible range of spectrum. The elements of which of the following groups will impart color to the flame? Now remember students, I have talked about the general properties of the alkali metal and the alkaline earth metals and all of those. Now your answer comes directly from that discussion. So 4 options are given here, or I would say 4 groups are given here. Now you have to say that which of this impart color to the flame. Okay. So do not take the bet of transition elements. Why I am saying it? Because for transition elements, I have said that the color of the ions are different. But here it is asked that which one will show colorful colors on exposure to the flame. So that's a different point of view, right? I think you got the point. So I'm saying that I told about the transition element that they have different colored ions. Okay, means their salts are of different color. It is not that they impart color to the flame, right? So take the example of crackers. They are also a type of what? Imparting color to the flame. If you just lit them, you will see various colors in the rockets. So similar to that, some of the elements, or I would say some of the groups, display various colors. We have already talked about this general property. So your time starts now. Remember, 2 options can be correct here. Your time is up. Now let us move to the correct answer. So the correct answer will be A and C. Okay, A and C will be the correct answer. Now why I am saying this? Let us try to understand this thing logically. Okay, so maybe it would be experimental part, but I would try to explain it logically. How? Let us see. So what is the reason for giving colors to the flame? First, we should try to understand that why some of the elements display color in the flame. So what happens whenever you heat an element? It absorbs energy, okay, in the form of thermal energy, and this energy absorbed by the element excites their electron to a higher energy level. So this is the first thing that happens as soon as we supply energy. Now second thing, what happens? Second part, since your electron has gone to a higher energy state, remember from the previous discussion of your structure of atom that if it will go to a higher energy state, it will come back to the ground state, and in that process it will emit light, okay, in the visible region. Now if I ask you, in your whole periodic table, which are the groups which is having your lowest ionization energy? Okay, if I compare all the groups, then which group is having the lowest ionization energy, or I would say from which element you can easily take out the electron? For that you must remember the trend. So 2 trends are there. If I talk about the group, then the ionization enthalpy increases from left to right. Okay, so what you would say about the lowest ionization energy? Which group will have the lowest ionization energy? out of all the group starting from 1 to 18, which one will have the lowest ionization energy? If it is decreasing from increasing from left to right, it will be group number 1 and 2. Okay, yes, it will be group 1 and 2. Very good. Now, if it is group 1 and 2, that means they are easily excited as compared to other groups because their ionization enthalpy is less. Means electrons can be easily abstracted from those elements. Now, if this is true, then for group 1 and 2, both we can say, okay, because this both are able to release electrons very easily because they are falling at the first 2 columns of the periodic table or the first 2 groups of the periodic table. Hence, they will impart color to the flame. So that is the reason, right? So 3 things are there. For the display of color, its electrons should be easily excited, and the alkali and the alkaline earth metals, they belong to the leftmost corner or leftmost column of the periodic table, and hence electron can be easily excited for them, and therefore they impart color to the flame. I guess this is clear to all of you, right? Now you can say that your option number A and C will be correct. Moving on to the next question. Remember, you have to pick up the correct statements. Okay, correct one. More than one can be correct. So your time to solve this question starts now. 4 options are given. So your time is up. Let us see what is the correct one. So a part of the question has already been discussed, I guess. We have already seen that the electron gain enthalpy, or I would say the energy released for the chlorine, is more as compared to the fluorine. So your chlorine is giving out more energy. Okay, so it should have a more negative value than your chlorine, than your fluorine. So this is than your fluorine. So this is already clear. If this is true, then all the 3 statements are correct. A, C and D. Okay, B1 is not correct. Let us see how. We will talk about each of these statements one by one. So don't worry if you didn't get it. Let us talk about the first statement. So this was the first statement. Helium has the highest first ionization enthalpy in the periodic table. So this is very correct. How? Now if you see the size, it is decreasing from increasing from top to bottom and decreasing from left to right. Just look at the periodic table by yourself if you have. So the first group will have the highest atomic radii and the last group will have the lowest atomic radii. Similarly, your first period will have the lowest atomic radii. If we take the common in both of them, then we can say that the helium has the smallest size, isn't it? Again, I'm repeating that part. So as you are moving from top to bottom, the size is increasing. That means the first group has the smallest size. From left to right, the size is decreasing. Therefore, your last group has the smallest size. You can clearly say from that logic that helium has the smallest size. Did you get my point? Now, if it is having the smallest size, then it becomes very difficult for us to take out the electron from the helium. Okay? To take out the electron from the helium, and hence it has the highest nuclear attraction to the electron. Therefore, this statement is correct that helium has the highest first ionization enthalpy in the periodic table. Now we have talked about the first statement. Moving on to the next one, B1. So what is the statement number B? That chlorine has less negative electron gain enthalpy than fluorine. So I guess you must not mistake this one, I guess, because we have already talked about it, right? We have said it that your chlorine has a greater amount of energy released. Now energy released means a negative sign. So if chlorine is releasing more energy, that means it has a more negative value of electron gain enthalpy as compared to fluorine. Now this sentence is just opposite of that discussion, that your chlorine has a less negative value. Okay, therefore it is incorrect. Now I think it is clear to the students that why this statement B is incorrect. So that this is an exception in case of electron gain enthalpy, that fluorine is having a less amount of energy released than the chlorine, and hence it is due to the small size of the fluorine. Therefore, electron gain enthalpy will be less negative than the expected one for the fluorine. Okay. So this is the statement number B. I guess this is clear to all of you that what is the reason behind the incorrectness of this statement. It is due to the small size, right? That is, fluorine is facing difficulty to accept the electron, and hence it is difficult for it to release more energy as compared to chlorine. Moving on to the next statement. So this is a very factual statement. We have already studied about this statement in the previous classes or in the general studies, that mercury and bromine are liquid at room temperature. So I am not discussing much about it. It is factually true. Moving on to the D statement. In any period, atomic radius of alkali metal is the highest. Okay. So I don't think we have to discuss much about it. We know that as we move from left to right, the ionization enthalpy increases. Okay. And as a result, the atomic radii is also decreasing. So this statement is correct. So what we can say, that atomic radius decreases from left to right due to increase in the electron in the outermost shell. Therefore, leftmost, being the leftmost part group in the periodic table, the alkali metal will be having the largest radii. Okay. So we can say that alkali metal has the largest radii in the respective period. So the part is that about the van der Waals radii. So when we'll discuss, so same, when we are considering the case of metals and non-metals, so what do we take for the metals? Do we take the metallic radii or the covalent radius? Which radius is taken in case of non-metals? Okay, yeah, metallic radii. In a case of non-metals, we take the covalent radius, right? So these are the two types of radius we take. Remember, while discussing this thing, we have already said that we will keep noble gas out of this discussion, because both of the radius that we have discussed so far, covalent and metallic, they are for the combined state. Okay, they are for the combined state, and as a result, we can't apply it to the noble gases which are not found in the combined state. Okay, so we will not consider this noble gas in this, right? No, you won't get any marks if you are not say considering one option. Also, you have to consider all the correct options that are possible. Moving on to the next question. All transition elements are D block elements, but all D block elements are not transition elements. So this is a very important question. So your time to solve this question starts now. Just try to analyze and think about the examples that belongs to the D block element but are not the transition element. So I'm leaving this thing to you. Meanwhile, I'm starting your timer. Okay. So 3 elements are there which are not considered in the transition element, although they are in the D block. Also try to think about the reason behind it, that why they are not considered in the transition elements. So this is also important to think. Okay, moving on to the next question, means answer. So what we know about the transition elements? What is the definition of the transition elements? Transition elements or transition metals are those which have an incomplete d subshell. Okay, so they have a incomplete d subshell in their neutral state or in their ionic state. So this is to be followed in the case of transition metals or elements. Then and then we can call it the transition elements. Okay. Now if this is true, then zinc, cadmium and mercury, these 3 cannot be considered as your transition elements. Why? If you say take the neutral state of these 3 elements, then they have a complete d subshell, okay, which is D10. And if you take their ionic state, then also it is having a complete d subshell, which is D10. So both for the neutral state and the ionic form, they have a complete d subshell. You can see here. So both are having D10, and in case of neutral, it is having D10NS2. Okay, I guess this part is clear to you, that why we do not call them as transition elements. But for this, you must remember that what is the most favorable, or I would say what are the oxidation states of zinc, cadmium and mercury. So they can exist in 2 forms. First is the neutral one, right? Second is the ionic form, Zn2+, Cd2+, and Ag2+. So from that analogy, I am taking the 2 states, right? The first state is having a complete d subshell, D10NS2. The second one, in which we have removed 2 electrons, in that also we are having a complete d subshell. I guess this is clear to all of you. So for your transition metal, you must have an incomplete d subshell in their neutral state or in their ionic state. Okay. Now moving on to the next question. How would you explain the fact that first ionization enthalpy of sodium is lower than that of magnesium, but its second ionization enthalpy is higher than that of magnesium? So your time to solve this question starts now. Just try to write the electronic configuration, okay, to figure out this question. Okay, so let us move to the answer. So first we will talk about the first ionization enthalpy. In this question, our main focus would be attainment of this stable electronic configuration. If you consider the first ionization enthalpy, in case of sodium, this is the electronic configuration, right? We have to remove 1 electron from here. Okay. If this is true, then what we can say? That it will easily lose 1 electron to become sodium plus. Now students, when we are saying that it can easily lose 1 electron, means we can remove electron easily from the sodium to make it sodium plus or Na plus. Okay. And therefore your first ionization enthalpy is less. So energy is what? Here the energy that we are supplying it to remove the electron. If after removing 1 electron, the sodium is going to stable electronic configuration, then it would be very easy to do so, because it will easily lose that 1 electron to attain the noble electronic configuration of neon. Okay. So that is the reason we are applying lesser amount of energy. I think you got the point. So what I'm trying to make here is that see, sodium is having one electron in the outermost configuration. Now if you remove this one electron, it will go to a stable noble gas configuration. Therefore, to do this process, we have to supply less energy. Therefore, its first ionization enthalpy is less than that of magnesium. Okay. So Na plus is having a noble gas octet. But this is not the case for the second ionization enthalpy. We'll talk about that. Now, if it is true, we can easily say that the Na is easily losing the one electron to gain the extra stability. And as a result, it is having a lower first ionization enthalpy. But in the case of magnesium, this is not the case. Because after removing one electron, it is still not going to any stable state. Now you will not take the case of half filled orbital, because I've already talked about this. You can't be predicting the stability in case of S subshell using the half filled or full filled one. So your magnesium is not going to any much more stable state as compared to the sodium. Therefore, it is not attaining a stable noble gas octet. And hence it is difficult to remove the electron in case of magnesium as compared to the sodium. So we can say that the first ionization enthalpy of sodium is lower than that of magnesium. I guess this first part is clear to all of you. Okay. So this is again an anomaly. So as we move from left to right, the ionization enthalpy increases. So sodium should have a lesser ionization enthalpy than the magnesium, but since your sodium is going to a stable electronic configuration, okay, so this is according to the general trend. This is no anomaly. Your second ionization enthalpy is already high, so it is becoming higher than the expected one. Now moving on to the next aspect of the question, which is saying that the second ionization enthalpy of magnesium is lower as compared to the sodium. So just take the opposite case now. If you take the case of second ionization enthalpy, in the case of sodium plus, so it is already in the stable form. It has a stable octet. So removing the second electron becomes difficult for the case of sodium. And hence it will require a larger amount of energy. Okay. So this is the reason your sodium plus is having a higher second ionization enthalpy. Now let us take the case of magnesium plus. So magnesium plus is not having a stable configuration. It is 3s1. But if you remove one electron from the magnesium plus, it will become Mg2 plus, which symbolizes the stable electronic configuration of the neon. As a result, since your magnesium 2 plus is going to the stable noble gas octet, therefore it is comparatively easy to remove that second electron, and hence it has a lower second ionization potential than the sodium second ionization potential. I guess this is clear to all of you. So both the cases. So in the first case, your sodium is having a lower energy because it is going to the stable oxidation state. In the second case, your magnesium is having a lower potential, or you would say the ionization enthalpy, because it is going to the stable state. Got it? Now moving on to the next question. The radius of sodium plus cation is less than that of sodium atom. Give reason. Now we have seen this thing, that the cation is always smaller than the parent atom. Now what is the reason behind it? Just think over it. Your time starts now. Okay, so your time is up. Let us see why it is true. So first of all, your cation is always smaller than the parent atom. The reason is that it has fewer number of electrons, but the nuclear charge remains same, means the same number of proton are present in the nucleus. So therefore your nuclear charge is remaining same. And hence it will apply more energy and therefore your size will reduce. So the atomic radius of sodium is 186. So you don't need to write this factual data in your answer. You just mention this part and you are good to go with the question. Okay. So for your information, I am giving this factual data that the atomic radius of sodium is 186 picometer. In case of the sodium plus, it becomes 95 picometer. So this is the reason why your cation is smaller than the parent atom of sodium. You can see it very clearly in this pictorial representation also. Moving on to the next question. Write down the outermost electronic configurations of alkali metals. How will you justify their placement in group 1 of the periodic table? So it's an easy one. So I am giving you some time to solve it. What you will take, n-1, n or n-2, if you are saying it as S1. So you can't say it as 0 to 1. Okay. You will never see an alkali metal having 0 electrons in the outermost shell. It is not possible, right? You take the example of any element, lithium, sodium, potassium, right? Say they will always have 1 electron in the S subshell. I would say valence S subshell, right? So you can't take it 0 to 1. Now, being that said, what we can write about the outermost electronic configuration? So they all have the similar outer electronic configuration, which is NS1, right? It is NS1. And what is N referring here to? N is referring here to the principal shell. Now, if I ask you, if you know the value of N, then can you predict the period number? So this is a question for you. Again, I am repeating it. So if you know the value of N for the case of, say your alkali metal, then can you predict the principal quantum number? Yes, you can predict it very easily. If I write the outer electronic configuration for the alkali metals, then this is the table for each of this. For the lithium, it is He, then 2s1. For the sodium, it is Ne, then 3s1, neon. For potassium, it is argon, then 4s1. Rubidium, it is 5s1. Cesium, it is 6s1. And francesium, it is 7s1. What is the period number for each of this? The first one is having a period number of 1. Then sodium is 2. Then your potassium is 3. Rubidium is 5. Cesium is 6. And francesium is 7. Okay, so this is sodium is 3 and lithium is 2. Right, so hydrogen is present in the first period. We can't take that. So this is the outermost shell configuration. And since they are having 1 electron in their valence shell, which is in the S subshell, you can say that they are placed in the group 1. Okay. Now we'll do a quick analysis of the mock test. Now we'll see the DPP, right? So this is the first question of the DPP. Which of the following statements correctly explains why the atomic radius decreases across a period in the periodic table? So 4 options are given here. What is the reason that your atomic radii decreases across a period? So first is principal quantum number increases. Second is effective nuclear charge increases. Third is number of electron shells decreases. And the fourth is the shielding effect increases significantly. So what is the reason for it? Why we are saying that their effective nuclear charge is decreasing? Okay, so the effective nuclear charge is increasing, and as a result, your size is decreasing, right? So I guess it's a easy one to guess. So the correct answer will be option number B. Moving on to the next question. Among the isoelectronic species, which one has the smallest ionic radius? O2 minus, F minus, Na plus, and Mg2 plus. So we know that the increasing order of size would be Mg2 plus. So since it is having the highest nuclear charge, so it will have the lowest radius. Then the Na plus, then F minus, and then the O2 minus. So this has the least value of charge on it, integral value. And hence we can say that the smallest one will be opposite one. Okay, so this is the opposite, this is the Mg2 plus. Option number D. Moving on to the next question. The first ionization enthalpy of boron is less than that of beryllium because boron has a smaller atomic radius than the beryllium. The electron from boron is a 2p electron which is less shielded than the 2s electron. The 2p electron of boron experience less effective nuclear charge than the 2s electron of beryllium. And fourth, boron has a high electronegativity than beryllium. So this is a tricky one, right? So there is a chance you would make a mistake in it. What will be the correct answer? So I'm seeing most of you are one answer only. So if more of you are attending the class, then you can answer it. So what is the reason that your first ionization enthalpy of boron is lower than that of beryllium? Okay, so I'm seeing answers as B. So that is incorrect. Okay, so that is clearly incorrect. Why I'm saying this? So take the case of beryllium. So do not try to just throw stones, right? So that is wrong to do. So take the case of beryllium. What are the number of atoms, electrons in case of beryllium? Hydrogen, helium, lithium, beryllium. Very simple, right? Simply write it 4. Okay. That means 1s2 and then 2s2. This would be the case. Okay. Any confusion in this? So here one electron will be present and here second electron will be present. Got it? Any doubt here in this part? Similarly, the outermost shell will have 2 electrons. So I'm explaining a very important thing, right? So just try to focus here. Now it may look simple to you, but it is quite difficult to understand for most of the students. Take the case of boron. Lithium, beryllium, boron, fifth one, 2s2, 1s2, then 2s2, then 2p1. Okay, so here one electron will be there. Here second, third, fourth and fifth. Since they are all in the same shell, they will be represented here, right? Now, when you are trying to say that they are less shielded. Now, what is shielding them? You are removing this electron, right? And in this case, you are removing this electron. What is shielding them? This inner, okay, this inner part is shielding them. This inner part is shielding them. Now, this inner part is similar for both of them, isn't it? You can see that both of them have a similar inner part, which is 1s2. Okay. Any problem in that? So both are having, so this shell is the thing which is shielding the outer electrons. I guess it is clear to all of you. Now, since the part which is shielding is same, therefore, the shielding experienced by both of them will be also same. So you can't say this statement that your 2s is less shielded than 2p or 2p is less shielded than 2s. So that would be incorrect. Right? Now the question comes, then what will be your answer? We have already seen that S, P and D and F. So in the case of NCERT, you not only need to learn it, or I would say not only need to see the concept, you must also understand that how you will apply that concept. So that is very important, application part. So this is the penetration effect, order of penetration effect, you know it. So S is present more, I would say closer to the nucleus, isn't it? S is present more closer to the nucleus as compared to P, since your, I would say the penetration effect is more. Yes, the right word is proximity. So S is in more proximate to the nucleus. Therefore, it will experience a greater nuclear charge as compared to the 2p electron. Okay, is it clear to all of you? Any doubt? Why I'm saying this? Since your S is present more closer to the nucleus, therefore it will experience more nuclear charge. Okay. Therefore your correct answer will be option number C. So if you have a doubt in this, you can ask now. I am saying that the inner part is same for both of them. So the shielding part is also same. But since they are present in different subshells, they will experience different forces on them. And therefore your correct answer will be C. Got it? Now you can say it in a different way also. We have seen that. We have already discussed it. Since your S is more penetrated, it will be difficult to remove it. And hence, it has a greater ionization potential. Moving on to the next question. Which of the following has the most negative electron gain enthalpy? Phosphorus, sulfur, chlorine and fluorine. Again, this is a repeated concept. Chlorine, yes, very good. So the correct answer will be chlorine, not your fluorine, because of its small size. The fluorine will have a lesser negative value as compared to the chlorine. Correct answer will be C. Coming on to the next question. The electronegativity of elements in the periodic table. So this is the easy one. So what is the order? In case of group and period, how does electronegativity varies? So electronegativity decreases from top to bottom and increases from left to right. So increases across a period and decreases down a group. That gives you your correct option as B. So this was all for today's lecture.